Okay, hello everyone. Thanks for having me in this conference. My name is Gonzalo. Topic of research that we do is about mobile robotics. So today I'm going to try to do a comprehensive presentation ranging from low-level sensors to high-level algorithms. Before I start, I would like to talk a little bit about us. So Skoltech is a university located here in Moscow. The idea is to have training and educating this next generation of scientists, technologists, and business leaders. We have our new campus almost fully operative, so here there's a picture. And more in particular about our research group. Well, there's one faculty member leading it. We have staff, PhD students, and our research objective is to deploy robots either in indoor or urban environments or outdoors and navigating the world intelligently. Okay, so this is high and long-term research goal, but how to achieve this? We need many different components, right? I'm going to try to divide them in two, mostly. So one is related to robot perception. Here, this is the fundamental question of how can you perceive the world? How can we understand it? And then how can we use, how can we process this on a meaningful way, right? So topics here include localization and mapping, SLAM. We also work with people detection and tracking because, well, at the end, part of this research goal is not just to create robots that navigate on their own, but they live in this very in the physical world, and this is inhabited by humans, right? So we definitely need to include people in the loop. We'll give some examples later in the talk. And the second research topic is about robot navigation, right? So here we have topics of path planning, dynamic environments, and this question could be summarized as after you have perceived the world, you need to execute a task. Mostly is how to get from point A to point B, right? Or solving other high-level tasks. These are kind of general questions, I would say, in the field of robotics. We offer a course on perception. We also offer another course on navigation. We have all material here in our webpage, or you can check out in our GitHub here in the slide. Okay, very good. So let's get started. Today, we have already discussed a lot about AI, machine learning, deep learning, training algorithms. So I'm just going to give like a little different perspective from the robotics field. Okay, so robotics needs this comprehensive understanding that goes from low-level sensors. We need to take into account that any observation comes from a sensor, right? So you cannot really abstract this. If not, problems or artifacts may arise. From these raw sensors that we are just perceiving the world or any state, we go to high-level algorithms, right? So with this information, we need to transform it, maybe process it end-to-end, right? So this is another approach that machine learning is doing a lot. Also robotics taking this approach from machine learning. But basically, this starts with the raw data. Now, what are the current challenges that we face mostly, right? So it's kind of part of them are also challenges in AI, but in particular for robotics is very important, these four. There might be more, right? But for mobile robotics, let's start with uncertainty. This is something that we can give for granted, but definitely it's not. The world is very complex. It's very hard just to start observing a scene and understanding what is there, even just create a simple representation, and after this, just making use of these observations that we have, right? So how to correctly characterize this? This is very complicated. There's always going to be problems, things that do not match exactly. It might come from sensor, it might come from your algorithm, it might come from other places, right? So uncertainty, it's something that we cannot take away. We can reduce it, but there's always going to be like parts of this complex environment that is the world that we will not be capturing correctly, right? Second very important topic is about robustness and safety, right? There's many points where things can go wrong. Imagine you have a navigating robot. You don't want to collide with people. If you don't have a robust algorithm, this could happen because of several reasons. Maybe you think the robot thinks that it is in a different place where it actually is, right? So this could result in potential dangerous situations. Maybe it's raw readings not working, right? And then you need to take this into account and just have a robust solution. There's many places, but the thing is that if really we want robustness, we need to ensure this in the whole pipeline, ranging from sensors to the high-level algorithms. Third topic is explainable AI. Why are we taking these decisions? In case of mobile robotics, it's clear we are navigating, but there's many components, and I'm going to talk about some of them later. That could be, for instance, how you detect a pedestrian. How do you think it was going to predict in the future? So that's why you were executing this trajectory and not this other one, right? So these kind of things are important. We cannot really just assume that policies are optimally trained and they are infallible. We need to understand what's going on. And this is also very important when we have people in the loop, right? And the fourth one is something that I think cannot be obviated, but it's really a problem. It's computational requirements. So these days, AI is taking more and more resources. Some models are growing. There's a lot of people taking a look at how to do this more efficient. But from the perspective of a robot, what we have is a limited system on board, right? So all these calculations or all these algorithms are going to be running on board. And the question is, you are not going to have full powerful server there running. So, okay, you can have like powerful machines, but there's going to be a limit. Okay, so still, we need algorithms that are not going to be computationally so heavy as many of the other algorithms out there, right? So this is another kind of extra dimension that we are adding. We want things to be working, deal with uncertainty, robustness, explainability, solving the task, of course, and on top of this, we want or we need low computational requirements, right? So it's not easy. Let me now just show very briefly what is the current paradigm in mobile robotics. We definitely need these two components. The first one is we need perception. We need to perceive the world. This is done by different means. So one could be we aggregate all information into a map, something meaningful later to be used. From this map we can localize, or it might be just raw information accumulated in a different way. At the end, it's this representation that is helping us to understand the environment. Okay, we humans, by the way, we are very good at doing this, right? So we take for granted many things, but robots are still struggling with this spatial understanding of these scenes, right? So localization has improved a lot, mapping a lot, but still understanding, well, this is, I think, active area of research. And then we have a second important component, that is decision-making or acting. Here we could be including planning, we could be taking control. And again, this is the current paradigm. There's a lot of research that is trying to mix the two together, getting deeper into one part, into the other, right? There's many alternatives, but let's say that just to have a canonical definition, it's going to be this one. So in this talk, I'm going to start discussing about low-level sensor data, and then we will shift to higher level task. In this case, it's going to be navigation and prediction of pedestrians, right? Why? You will see that, as I said, errors could be accumulated even from raw sensors or from your algorithms themselves, right? So mobile robotics is trying to deal with all these issues, right? We cannot really ignore some of them. Okay. Let's start with this idea that we can consider a robot just kind of a network of sensors. It has other parts, right? So maybe more complex robots, include mechanisms and other issues. But the simplest definition would be this is just a moving point. For instance, these two robots that we are showing here in this slide, one is the Akula robot. It's simply a wheeled robot. In this case, we are using LiDAR, which uses laser just to estimate how far away are objects. And we could be using a camera. Right, so we have two sensors here. Sensors is adding robustness. The problem of using several sensors is how to fuse them. This creates some artifacts at the same time. And we have another example of maybe not robot, but kind of sensor networks, that is this bandeja robot. What we have here inside is also like a set of sensors. In this case, we were very interested in investigating about smartphones as raw sensors, not industrial cameras that you can buy and you can deploy. But the idea was, okay, let's use smartphones because these are massively available for everyone. It has a lot of interest because they are already there. And maybe what we need to do is apply a little bit our algorithms to be working with smartphones as well. So in this case, this robot was dealing more with the perception part. There's no actuation here. It's just imagine a moving mobile phone, just a little bigger. And then it had extra sensors, like a depth camera and some IMU. Okay, so the problem comes when, yes, we really want to use mobile sensors, mobile phones as sensors, but by themselves they are a system. And it's a system that it's not so easy to access. There could be other examples of these kind of systems, but at the end what happens is that we have, for instance, a depth camera that works in a time reference and a mobile phone that has its own operational system. And we still want to use this data, right? So what happens when you just directly apply what you get from the camera on the mobile phone and what you get from depth? So it's this kind of problem. You see this little shift on the image on the left. Yes, what is happening is that there's a delay. The camera is moving with, it's shooting its images with some frame rate and at some given time. The mobile phone is doing the same. And we don't really know what is the time difference between the two systems. So the first very important task when we start aggregating different sensors from different systems is to do proper time synchronization. So this little shift on only some milliseconds is enough to really get bad results when you are trying to do this perception, this aggregation of observation from the world into your map, right? So this little shift is going to create like misalignments and other artifacts. What we want is something like what we have on the image on the right. So this is after some millisecond alignment. And with this, what we have is that both sensors were shot at the same time. Okay, how did we do this? Here we have our lab members that were collaborating on this project. What we did is, because we had a rigid body just containing the two sensors, we were using this principle of twist and sync. So the idea is very simple. You twist the platform, we create a common signal on both systems, and then we just align them based on the cross-correlation. This signal, by the way, was created with IMUs, which is also some readily available sensor. You have this on your mobile phone. This is also typically used on quadcopters, wheeled robots, many places. It's also very cheap, and let's say the industry is very interested in making these sensors more reliable and more accurate as time goes by. And with this, we can get a very accurate reference of both time references. Okay, so let me give just a couple of examples. Okay, this was supposed to be a gift where things are animated, and what is happening is that we have the two mobile phones as in this image. We have two mobile phones, one very close to the other. And then we were taking images after doing proper time synchronization. This also has a little caveat that it's not just time synchronization that we need, but also phase alignment. So this means that both applications are shooting at the same time. So this is video stream. Anyway, what was happening is that we had high dynamic scene. For instance, someone just throwing snow here in Moscow in December. And well, we were able to capture with the two cameras exactly the same event. And if you see these images, these are flowing pieces of snow, right? Flocks of snow just going away. And we could really achieve like very precise things. So it looks like static image. It's not that this object is like this. It's that they were flying, right? And well, this is an example of how we were capturing. So this is the camera there on the image on the bottom. And on the right, we see another example of how we can use like this kind of enhanced mobile phone just to record people. So in this case, we wanted to get information from people. And well, a good thing is why don't we just create like enough views from a mobile phone enhanced with a depth camera. So this project was about this. It's only possible then to get like meaningful data if things were well aligned. So that's another motivation. Another example, so this is a little in line with what I was saying. When you capture all this information, let's say in this semicircle trajectory, you want to build representations of the map, right? Representations of the environment. In this case, what we are doing is something that is called SLAM, also could be known as structure from motion. We are taking all these images, aligning them together to create a comprehensive and representation in 3D of all these points. So you see all these key points that are in red are just very salient points. If you observe all of them as you are moving, then you can create kind of this aggregated map of the environment. In this case, we were interested in getting portraits of people. So there's an extra component of difficulty that is people move a little bit. Even if you try to stay still, you're going to move a little bit. So this was an example of just the perception part on the mobile robotics that we are using. Yes. What can we do now with these kind of scenes? So these two images are the result of aligning all these images obtained from the mobile phone. We get like kind of this 3D point cloud, so a lot of points obtained from the sensor, and then later we were doing estimation. So maybe an example of how we can use this, it's not really for robotics. Maybe we can do this just to do representation of scenes or 3D objects. Or maybe we want to synthesize or render portraits in other kind of domains, right? So at the end, I think these technologies are not just exclusive for robotics. We definitely contribute here. There's other fields, computer vision, graphics, that also work on this problem. Let's give last example about the multiple smartphone alignment. So in this case, what we have is two smartphones taking not together, but in any kind of position. And what we were doing is, well, this video was showing Dinar here, jumping, but this was a dynamic scene, right? So if we have synchronized, well-synchronized video stream, we get examples as in the image on the center, right? There's no artifacts, there's nothing wrong. If they are not time synchronized, then what we see some artifacts as this image on the right, right? So you see that the leg, it's kind of duplicated. Okay, so this application of video stitching, if you are curious, you can check out our GitHub, because this application is ready for everyone to try. You can just take a couple of mobile phones. We tried this with 40 different models, and synchronization that could be achieved was really high. And well, let's say that this is just a way how to transform a smartphone that is not really designed for this to be the right sensor to be used in robotics and other perception applications. Okay, another interesting question that we were asking is, after we solve this problem, how can we know that this solution is good? Let me explain this. After we go around this person, we are getting like positions, previous positions of the camera. So how can we know that this solution that we have calculated is good? Usually what we have is a more expensive system just answering this. For instance, examples of these are motion capture systems that are used in movie making and other things that are really capturing at sub-millimeter precision, like positions of reflective marks. There's other solutions for this. If you want to take if you want to get the geometry of, for instance, room, you could be using industrial-grade LiDAR. So this is basically very accurate LiDAR that gets a lot of points, and all of them are going to be very precise. Others could be just using GPS-like systems. And in general, maybe they will not be available. So with this, what we wanted to say is, what happens if we have a trajectory? We don't have these expensive systems there to tell us if we were like really getting like a good solution or not. But still, we want to answer the solution if we want to answer this question if this solution that we have calculated is good. Okay, so well, very briefly, I'm going to introduce like the idea behind. We can aggregate all the information and then look at the consistency of the map. Okay, so if we do this, usually this gives you a measure, and this measure doesn't mean that it's going to be correlated with the error in the trajectory. So what we are looking for here is a metric that is relating like how good this map looks like with how much error we are doing as this trajectory is estimated, right? For this, it turns out that we just need to select a subset of these points, right? We only select those that are orthogonal for reasons, well, basically, well, if not, they will not be correlated with trajectory, and more details on this I'm not going to present today. But with this subset, then we have a good measure that is telling us, just by how this map looks like, how well our trajectory is. And I think this is a very important question because there's not going to be always available these very expensive systems that are going to help you, right? So maybe you just want to take data just right here, because you have decided, you have these sensors, your mobile phone, but you don't need to have like these very expensive certifying systems, right? Okay, so this is just an example, this very famous data set, Kitty. So we were just evaluating this, like which points on this data set, which by the way is supposed to be giving you ground truth. You cannot really trust so much the ground truth, right? So you see like points here like in orange. Okay, maybe if you didn't hear about this Kitty data set, this is kind of obtained just by car with a lot of sensors, and this is for autonomous driving, but this is kind of a default data set used yes, for localization, for mapping, for odometry, and for many other tasks. Okay, I'm going to try to go briefly into these kind of now high-level algorithms. We have discussed a little bit about data, and I hope that I have convinced you now like how important it is to generate like data that is well aligned and doesn't have any artifacts. And now let's see an application of, we get this data, we process, and the task now it's going to be about human motion prediction. So we are with this mobile robot in an environment, urban environment, with other pedestrians. We are detecting them with cameras, with depth images. It's not important for now. But the thing is that with human motion prediction, we can also use this for downstream tasks. It could be like navigation, robot navigation, activity recognition, and many others. Okay, so important way of understanding what's going on. Again, these environments are very complex. Imagine they are crowded by many people. is that just to have like accurate predictions, a possible way of understanding this is if we break down the problem in two, right? So the first one is we do intent prediction. We can divide any urban or indoor environment into a subset of goals, and then the first problem is going to be infer which are these goals, right? So what is the importance of intent? Well, here there was a graphic showing that if you just do first order approximation of what is your prediction, you get very accurate predictions with very short instant of time. So that means that if you are moving and you just keep this velocity as constant, or you do any other simple methods that do not account for goals, you're only going to be accurate for short periods of time, like less than a second. If you take goals into account, then the prediction, the quality of the prediction you are doing increases, and increases for longer horizons than 5 seconds. So this is great. An example of this is I'm moving for 1 second. It's clear that I'm just going to keep my velocity, but what's happening next? And I think for this we need to think about the environment, right? So this is why dividing the problem into goals makes sense. This is another example of visualization of human motion prediction. You see here, like with this red kind of distributions or heat map, if you want, like what are the future predictions, future positions that any pedestrian is going to look like. And well, now let me talk very briefly about more modern techniques that we have developed also. So it's important to have goals, right? But I think we all agree that data-driven approaches will give, like, for most of the problems, better performance. So the same is true for human motion prediction. In this case, what we have is this architecture, as I was defining. We calculate our goal. Here, our estimator is a neural network. And then the other problem that we observe, and this has to do with uncertainty, is that most of the algorithms for doing prediction tend to be overconfident. So what it means? That they give you a prediction and that they tell you that they are very confident of what's happening, right? And this is usually a mistake, because if you overfit, if you think that your prediction is going to be exactly what is going to happen in reality, this creates a lot of artifacts in later stages. For instance, for planning, if you want your robot to move, some of these things have to be taken into account. So in this work, what we were doing is just removing this part of this overconfident of prediction systems. We were properly training, taking this into account. So we were proposing a metric. And at the end, what we get is algorithm that is similarly in accuracy, right? But it also considers like this uncertainty properly. Okay, this could also be applied, by the way, to vehicles and autonomous driving. So the same algorithms and the same problems that I have discussed applied. And just to summarize, if I have 1 minute, I would like to say that I gave today this complete view about robotics, mobile robotics, right? From low-level sensors to high-level algorithms. I didn't go like a lot in detail into planning and other navigation, but I think the problem on prediction is very illustrative as well. The quality of data matters, so we cannot just take a lot of sensors, put them together, and hope that our networks are just going to figure it out by themselves what to do. You need to properly take care of this, right? So sync, time sync, addressing uncertainty, all these issues require attention. And well, mostly I've talked about uncertainty, but this goes across all levels, right? So this is something that I would like to say that it's currently an issue, a bottleneck, why we are not deploying robots everywhere. So uncertainty is one of the problems. The others I already discussed. All right, thank you very much. This is my contact. And
thank you very much for your participation. It was a very interesting report, and it was really nice to have you here on this stage. Thank you. Bye-bye.